All right, today we're diving into one of the absolute game changers in data science, dimensionality reduction. You know, it's all about taking that messy, chaotic data and turning it into something crystal clear. So let's jump right in.
So let me ask you something. Have you ever opened up a data set and just stared at it? I'm talking hundreds, maybe thousands of columns, and you just feel like you're drowning in information. If that sounds familiar, you're definitely not alone. It's a massive, massive challenge we all face.
And that right there, that feeling of being overwhelmed brings us straight to the heart of the problem. You think more data is always a good thing, right? Well, not exactly. The real issue is often having way too many features, variables. It turns out more is definitely not always better.
And here's why that's such a headache. When you have too many features, everything just slows down. Your computer starts to crawl. Trying to visualize the data? Forget about it. And worse, it can totally mess with your machine learning models. They start to overfit, and that's a huge trap. Think of it like a student who just memorizes facts for a test but has zero real understanding. They can't answer a single question that's phrased differently. It's all part of this infamous problem that data scientists call the curse of dimensionality.
But don't worry, it's not all doom and gloom. Because for every big, scary problem in data science, there's usually an equally clever solution. And in our story today, the hero swooping in to save the day is dimensionality reduction. This is how we fight back against that curse.
So what is this thing really? Well, at its core, dimensionality reduction is just the art of smart simplification. It's about taking this massive, bloated data set and, well, squishing it down. The whole idea is to intelligently throw out all the junk, the noise, the redundant stuff, and hold on tight to the critical information, the stuff that actually matters. It's all about finding that signal in the noise. Now, there are basically two main ways to do this. First, there's feature selection. I like to think of this as packing for a trip. You look at everything you could take, and you only choose the absolute essentials. Then there's feature extraction. This is way cooler. It's like taking all your clothes and inventing some brand new, super efficient, multi-purpose travel gear out of them. And for our purposes today, we're going to focus on that second one, the really transformative approach. Okay, let's get into our first major technique. It's called Principal Component Analysis, or just PCA for short. And honestly, if these techniques were superheroes, PCA would be the super strong, ultra reliable one. You know, the one you call in for the really big jobs. And here's the really crucial thing to get about PCA. It doesn't just pick the best features from your list. No, it actually creates brand new ones. It takes a look at all your original data, things like a customer's age, their income, their spending habits, and it intelligently combines them into a smaller set of super powerful new features. We call these principal components, and they're basically a super condensed summary of the most important patterns hiding in your data. Now, the math behind it can get a little heavy, I won't lie, but the actual process makes a ton of sense. First, you standardize the data, basically get everything on the same scale, so you're comparing apples to apples. Then, the algorithm figures out which features tend to vary together. From there, it finds the main directions in the data where the most change, the most information is happening. And finally, it just ranks those directions by importance and uses the top few to create our new, compressed features. Simple as that, conceptually. And this is where the magic really happens. Just think about this for a second. You could have a data set with 100 different features, 100 columns, and with PCA, you could shrink that down to just 10 new components and still keep 95% of the crucial information. I mean, that's not just an improvement, that's a massive, incredible boost in efficiency.
Okay, so if PCA is our powerhouse, our workhorse, then our next technique is more like the artist. Let's talk about TSNE. Its whole reason for being is to make your data not just smaller, but visually beautiful and easy to understand.
So where PCA is great at finding those big, straight-line patterns, TSNE is different. It's what we call a non-linear technique. That just means it's built to find the really twisty, intricate, hidden clumps and relationships in your data. And then it lays them all out on a simple 2D or 3D map that our human brains can actually look at and make sense of. It literally makes the invisible visible.
And how it works is actually surprisingly intuitive. Just imagine you're at a huge party. TSNE is like the ultimate party planner. It first goes around and figures out who's close with whom. Then it tries to arrange everyone on a little dance floor. The goal? Make sure close friends are huddled together and people who are basically strangers are pushed far apart. What you end up with is this perfect visual map of all the different social circles in the room.
And this is exactly why data scientists get so excited about it. When you run T-SNE, you're not just getting some boring chart. You're getting genuine insight. It creates these gorgeous, super clear clusters that let you just see the structure of your data instantly. It's something that just looking at rows and columns of numbers could never, ever give you.
All right, so we've got the powerhouse, PCA, and the artist, TSNE. But how do they actually stack up in the real world? Let's put them head-to-head and figure out when you'd reach for one over the other.
Okay, so here's the simplest way to think about it. PCA is your big picture tool. It's for seeing the entire forest and understanding its overall shape. It's all about preserving that global structure. TSNE, on the other hand, is for getting up close and personal with the individual trees. It's a master at uncovering those tiny, local clusters and all the super fine-grained details.
And this breakdown really makes it clear. You can see PCA is linear and fast, and its results are pretty easy to interpret. That makes it your go-to for prepping data before you feed it into a machine learning model. TSNE, it's nonlinear, it's a bit slower, and it's all about that visual aha moment, not so much about precise interpretation. So here's a good rule of thumb. Use PCA for building models, use TSNE for exploring your data.
So where does this stuff actually get used? Well, take banking. Analysts use TSNE to look at millions and millions of transactions all at once. And what they find is that fraud often creates its own weird little cluster, totally separate from normal activity. It just pops right out on the visualization, making it so much easier to catch.
Or how about retail? A company can use PCA to take hundreds of data points about you, what you buy, how long you browse, where you live, and boil it all down into a few key customer profiles. Then they can create marketing that's way more targeted and, frankly, way more effective.
And this one's huge, healthcare. Think about genetic data. It's unbelievably complex. But researchers can use a technique like TSN to visualize it and actually see how genes are behaving differently in people with a specific disease. We're talking about finding patterns that could literally lead to breakthroughs in new treatments. It's incredibly powerful stuff.
Okay, so let's wrap this up with the key takeaways. First, dimensionality reduction is your secret weapon for turning data chaos into clarity. Second, doing this helps speed up your models, cuts through the noise, and helps you avoid that nasty overfitting problem. And finally, remember, PCA is your fast, reliable workhorse for building models, and TSNE is your specialized artist for visualizing and exploring those hidden patterns.
And that really just leaves us with one final big question. I mean, we live in a world where data is just exploding. It's growing exponentially. The tools we talked about today are amazing, for sure. But it really makes you wonder, right? As our data gets even more complex, what new dimensions of understanding will we need to conquer next? And what kind of tools are we going to have to invent to even begin to make sense of it all?